So this is Dr. Mark Barkey, Professor of Aerospace Engineering and Mechanics at the University of Alabama. I'm going to talk a little bit about yield surface plasticity. And this wouldn't be where I would start a class in plasticity, but I'm going to do these videos and maybe I'll backfill with a little bit more background information later. So I'm going to assume that you have a little bit of basic knowledge of index notation, basic calculus, first and second order tensors, analytic geometry, and basic yield criteria already, such as the von Mises Criterion, otherwise known as the J2 yield theory in particular. So with that in mind, let's just kind of jump in and talk about what a yield criterion is and give an example. So if you were a student in mechanics materials or machine design, you probably talked about something called the von Mises yield criterion. And so that says that if you compute something called the von Mises stress, I'm not going to derive it right now, but I'm just going to write it down. The von Mises stress is a combination of stress components that I have here. It's the differences among the normal stresses squared. It's usually written this way, plus 6 times each of the shearing stress components squared, all to the 1/2 power. And if that combination of stresses resulted in a value that was greater than the yield stress of your material, then your material yields, according to that theory. Now we're going to start off with some basic things, assuming that we have an isotropic material and so forth. What we're going to talk about can apply to isotropic and anisotropic materials, but we just need to start with something that we can wrap our heads around first, then we can add some complexity to it. Now there's another way to express this. It's more of a functional form. So instead of saying if the von Mises stress is greater than or equal to the yield stress, then it yields, I'm going to take and I'm going to square both sides of this expression and say that we have a function of the stress is f. If that is, well, let's say exactly equal to, we're going to be right now talking about just at yielding, equal to the yield stress squared, then we have yielding. And let's see what that equation would look like. If I square both sides, of course I have 1/2. And these terms right here, sigma x minus sigma y squared, and so forth. I'm just going to go ahead and continue to write these down just so we can see the equation right here. But I'm going to do one extra thing. And the reason for doing this will be a little bit more clear later. Typically we assume the symmetry of the stress tensor when we have conservation of angular momentum in our material. But in more general terms, and it's going to be more clear later when we start taking partial derivatives of our yield function, it's, in my opinion, a lot more convenient to think of the shearing stresses as being tau xy being different from tau yx. So I'm going to write it this way: 3 tau xy squared plus 3 tau yx squared, and so forth. Let's see if I have enough room. Okay. So that's the F part, and then I could write this as equal to sigma yield squared, but I'm going to do something different. I'm going to move the sigma yield squared over to the left-hand side and then set the entire expression equal to 0. And this works out really nice. In computers, you can program all these things in. You can evaluate your yield function, take it minus sigma yield squared, set that equal to 0, and determine whether or not you are yielding your material or not. If you've not yielded your material, then we just use 3D Hooke's law to relate stresses and strains. If we are yielding, if we have met the yield condition, then we have to go through finding out what the plastic strain increments are. And that's the purpose, that's the whole utility to multiaxial yield surface plasticity. Well, let me make a little bit of room, and let's talk a little bit more about this yield function. Now, our purposes are going to be suited a little bit more at this point if we multiply out some of those squared terms for the normal stresses. So let's get a start on that. So I'm going to have from the first term sigma x squared, and then I'll have a minus 2, and then a product term sigma x sigma y plus a sigma y squared. And let me go ahead and write the rest of these out. And you see with the second term we're going to get another sigma y squared, so we'll end up with 2 of those. And then likewise we'll get 2 sigma z squareds from that contribution. And I'm going to have to continue this down on the next line with the shearing stress terms. And I won't do this a whole lot more, but for now I'm going to go ahead and write down all of these different terms. That would be a zx squared, and then the last one 3 tau yz squared and 3 tau zy squareds. And of course now I can multiply or divide that 2 through each of those terms in that expression. And let's just go ahead and do that too. So I'm going to group my sigma x term. I have 2 of them. I divide by 2. I'm left with 1. And then I have 1 of these. And 1 sigma z squared. I'll end up with a minus a product term sigma x sigma y and a sigma y sigma z, and then I should have a minus sigma x sigma z. Okay, and then I'll have plus the 3/2 these various shear stress components squared. Now at this point we're going to think of this equation in a slightly different way. Instead of just being a function that's sitting there that we plug numbers into, if we look at the form of this equation, this is an equation of an ellipse in terms of 9 terms. So you may be more familiar with different equations of an ellipse. Maybe in a plane you have ax squared plus by squared is equal to some kind of number squared. But this is an ellipse in 9 dimensions. We call that a hyperellipsoid. And that would be in stress space. So instead of having coordinate axes of x, y, and z, we're going to have coordinate axes of sigma x, sigma y, sigma z, tau xy, and so forth. So we're going to have 9 components. And the geometrical nature of what we're doing is really important to getting a good feel for what goes on in these hardening rules and in multiaxial cyclic plasticity. It's you can do it purely mathematically, but I think understanding the geometry really aids in understanding the development of different yield criteria and flow rules throughout the years, and maybe even the development of your own yield criterion or flow rule for your particular material. So let me make a plot. Let me make a little bit of room. I'll make just a sketch of what this thing might look like in hyperspace. Well, now obviously I can't draw this function in 9 dimensions, and so what I'm going to do, I'm going to cheat. I'm just going to draw it in 2D. And I know it's going to be some sort of ellipse, and so, I'm just going to draw it like that. There are certain things that we haven't talked about, but hopefully that'll be in either a video that should go prior to this or later than this in the playlist. We're talking about Drucker's maximum dissipation postulate and the shape that the yield surfaces can take for work hardening materials. But suffice it to say that it's going to be a convex yield surface. We don't have any things dipping into the yield surface. It's going to be pushing out. It might look like an egg, it might look like an oval, it might look like an ellipse, but it's not going to look weird where things intrude or protrude into this yield surface. And so I'm just going to label this thing as F, and this would be F of my stress tensor, and this is my hyperellipsoid, my just geometric representation of my hyperellipsoid in this 9-dimensional stress space. Now the utility of representing this yield function this way is that if I have my stress value, my yield stress value known, let's just keep things easy. If my yield stress is 100 megapascals, then from the origin of my stress space, any point that lies on the surface is an equal distance metric from that origin, and it's going to be a value of 100. So anytime I evaluate the function, no matter what my combination of stresses are, if I lie on this surface, this will evaluate out to be 100, or in this case 100 squared, such that when I take minus 100 squared, my yield stress, I will end up with 0. Now the problem with this yield surface right now, and it's not a huge problem, it's a little bit inconvenient geometrically, is that it is an ellipse, and it's an ellipse that has a tilt in the sigma axis, but it doesn't have a tilt in the tau axis. So if we looked at pure tau, it would look like a circle with a certain radius, but if we looked at a plane in, say, sigma x and sigma y, it would be an ellipse. And that's not a huge deal, and a lot of the things that we're going to talk about when we get into anisotropic materials, we'll assume that we have an elliptical shaped initial yield surface. But for now, we can do some things that are a little bit easier than that if we look at something called deviatoric stresses. So let's write down our stress tensor. And, I'm going to use a variety of notation. Let me go ahead and keep using taus for now. Later on, I'll use numbers instead of x's and y's for my subscripts. But for now, let's just keep with this notation. And again, I'll write this as if it's non-symmetric. We will take advantage of the symmetry when we have it. But there is the components of my stress tensor. So I can't emphasize enough that this hyperellipsoid is a very nice geometrical representation. Now I did mention, before we get into deviatoric stresses, I did mention that our points on the yield surface have this equal value of sigma yield, whatever our yield stress value is. But another interpretation is if we come up with a combination of stresses that is not causing yielding in the material, then that combination of stresses lie inside of our yield surface. In other words, if we're inside the yield surface, then we have our elastic stress state. And if we're on our yield surface, then we are at the verge of yielding. Now, you might say, well, if we go outside of our yield surface, then we have plasticity, we have yielding. Well, we're going to be a little bit careful about that. We're going to start now. In multiaxial yield surface plasticity, we're going to end up saying that we can either be inside of the yield surface or we can be on the yield surface, but we're not going to be able to be beyond the yield surface. We're going to end up having to grow our yield surface or move our yield surface so that our stress point, our current stress point, is always on the surface of the yield surface. And that'll be a little bit more clear later when we talk about kinematic and isotropic hardening. Okay, so again, we have an ellipse in 9-dimensional stress space, but we're going to do a transformation to turn our ellipse into a circle, and we're going to do that by using something called deviatoric stresses. Now, if we have a stress tensor sigma ij, we can come up with the deviatoric stresses as Sij equal to sigma ij minus Kronecker delta ij 1/3 sigma kk. Now, if you're not familiar with index notation, maybe I can put up a video on index notation, but ij is the component like x, y, or xx, and Kronecker delta ij is a number. It's either 1 or 0. It's equal to 1 if the index I and j have the same value. It's equal to 0 if they're different. And what sigma kk means is that it's the trace of the stress tensor. And sigma 1,1 plus sigma 2,2 plus sigma 3,3, it's the diagonal terms, and then divided by 3. So if this was my stress tensor, my deviatoric stress tensor in this case would look like this. Where all along the diagonal we're subtracting off something called the hydrostatic stress. The hydrostatic stress is just going to be the average of the 3 normal stresses. Okay, so this in index notation, and this term over here in the 2-dimensional matrix form of the tensor, those are equivalent. Okay, so let's see what happens when we write down the von Mises yield criterion in terms of deviatoric stresses. Okay, so in this case, the von Mises yield criterion, and I haven't derived this here, but again, I will try to do that in a separate video. The von Mises yield criterion reduces down to 1/2 Sij Sij, where we're using summation notation for subscripts. 1/2 Sij Sij is equal to k squared, where k is proportional to the yield stress of the material. We'll find out what that exact relationship is pretty soon. But this is also known as the J2 theory, or J2 criterion. And what that is J2 is the second invariant of the deviatoric stress tensor. You may know from linear algebra that for a second order tensor or a matrix that you have, like a 3x3 matrix, you have 3 invariants. You have the first invariant, which is the trace. You have the third invariant, which is the determinant. And then you have the second invariant, which is it's the sum of the invariants of the cofactor matrices. Sum of the determinants of the cofactor matrices. And in this case, in terms of deviatoric stresses, it turns out to be 1/2 Sij. Now, if we were to expand this out, because this term right here, the way that we interpret that, in case you're not familiar with index notation, whenever we have a repeated index like I or J, that means that we have an implied summation on those values. We can only do this if we have a pair of repeated indices. 3 is ambiguous, and if we only have one, that's called a free index. But if we have these repeated indices, they're called dummy indices, and we can expand this out. And so we have a half, and so 1, 1, 1, 2, 1, 3, 2, 2, 2, 1, 2, 3, and maybe 3, 3, oops, 3, 1, and 3, 2. See if I have 9 terms there. Okay. And hopefully don't have anything repeated. All right, so we have this. And if I bring the k to the other side, I can make this equation equal to 0. And now, if I want, I can multiply both sides by 2. We'll see there's times where we want to do this and where we don't want to do this. But for our purposes right now, let's go ahead and do that. And I'll just put these things as squared terms right now. And if we look at that, geometrically, that's the equation of a hypersphere. We don't have those cross terms like we did when we looked at regular stress space. So in deviatoric stress space, where we have, instead of x, y, and z axes, we have S, 1, 1, S2, 2, S3, 3, and so forth, in 9-dimensional deviatoric stress space. The von Mises yield criterion plots as a circle or a hypersphere. So in a similar way that I drew a little schematic of my yield surface in regular stress space, I can draw a nice yield surface. Well, I can draw a circle, pretend that's a circle. I can draw a nice circular yield surface in deviatoric stress space. And I can still have the same ideas where I have a center of the circle, and any point on here is equal distant from now the center and has an equal value of my function. Now, I guess if we wanted to be particular, we could call our function a different letter. I used f, so maybe we can call g, but suffice it to say that it's the same thing. If I just call this a function f of my deviatoric stresses, and it all has the same radius, if you will, k times the square root of 2. And some of the geometry that we're going to do is a little easier to evaluate in deviatoric stress space. And you're going to see me kind of go back and forth between regular stress space and deviatoric stress space as I talk about these hardening rules and flow rules. So hopefully that won't be too confusing, but you kind of need to look at the context of what I'm talking about and what I'm putting into my yield function to determine whether I'm talking about yield stresses or not. Before we get too far along, let's go ahead and figure out what that value K is in terms of the yield stress of our material. And when I say the yield stress, I'm talking about the uniaxial tensile yield stress. That's a pretty common number that we're familiar with. So we know that when we're in a tension test, we have a uniaxial state of stress, and let's say that this component of our stress is equal to the yield stress and everything else is 0. We don't have any stresses in any of these other directions. And with our definition of the deviatoric stress as sigma ij minus 1/3 sigma kk Kronecker delta ij, our deviatoric stress tensor then would look like sigma yield minus the hydrostatic stress, which is 1/3 of sigma yield, zero in these other places, and then zero shearing stress here. We would have minus 1/3 sigma yield and minus 1/3 sigma yield. So this would be S11, S22, and S33. So if we put these values in here, let's see, that would be positive 2/3. So we have 2/3 squared sigma yield squared. Now that's 0, that's 0. We would have minus 1/3 squared sigma yield squared. And then zeros for the shear terms, and then another minus 1/3 squared sigma yield squared minus 2k squared is equal to 0. So let's see what we've got. We got 4/9. When I square it, that's a positive, that's another 9th, and then another 9th. That's 6/9. And this is all times the yield stress squared. If I divide both sides by 2 and solve for k squared, what is that? 3/9. And if I take the square root, well, 3/9 is 1/3. Let's do that first. This k, as I've written it here, would be the yield stress divided by the square root of 3. So we'll keep that in mind, and we'll pull that out later when we need it. All right, so we talked a little bit about the von Mises yield criterion. We've talked about stress space and deviatoric stress space. What I'm going to do in the next video is to talk about something called the radial return method, where we look at a point that has exceeded the yield stress of a material, and we want to bring that and scale it back to our yield surface. So we'll do the radial return in part 2.